Hey friends, welcome. Today we are going to discuss the kinetics of trimolecular reactions. Now, basically, trimolecular reactions are those reactions which involves the formation of activated complex wherein three reactant molecules they combine to give or they combine to form an activated complex, and further the reaction will take place. So there are very few examples of trimolecular reactions, only handful of examples of trimolecular reactions, and all these reactions are basically elementary reactions, and it is also considered that no side reaction will take place while considering those trimolecular reactions. So there are only 5 homogeneous gas reactions that are definitely known for the third order, and all these reactions involves nitric oxide as one of the reactants. So we'll first see one by one all the examples, and then we will move on towards its kinetics. So the first reaction was given in 1914 by Trotz, and he studied the reaction between nitric oxide, that is 2NO, and it reacted with chlorine to give 2NOCl, that is nitrosyl chloride. He observed this reaction at different pressures and at different time intervals, and he proved that this reaction was a third order reaction. The second reaction that was given was in 1918 by Bodenstein, and he also studied the reaction between nitric oxide and oxygen molecule, that is 2NO and O2. So it gave nitrogen dioxide, which is also a third order reaction. So he studied this reaction by immersing the vessel in a constant temperature bath, and then he observed the change in pressure with respect to time, and he concluded that this reaction was a third order reaction. The third reaction was again given by Doctors and VP Dalal again in the year of 1918, and they also reported the similar type of reaction wherein this chlorine was replaced by bromine, and we had 2NO plus Br2, so it gave 2NO Br. So this was the third reaction that was reported. Then the fourth reaction for the trimolecular type was reported in 1926 by C.N. Henselwood and Green, and the reaction was between again nitric oxide and hydrogen molecule to give dinitrogen oxide and water molecule. And this reaction, it takes place only at very high temperature. And the fifth and the final reaction that is again reported in 1926 by again C.N. Henselwood, again wherein they, instead of using hydrogen, they utilized heavy hydrogen or deuterium to give the reaction, that is 2NO plus D2. Again we will have NO2 plus D2O. So these are the 5 homogeneous reactions which follow the third order kinetics, and I don't know, probably there may be few more reactions till now, because this is around 1926, and there may be few more reactions reported which followed the third order kinetics, but these are the 5 classic examples of the reactions which are following the third order kinetics, and all these reactions are the examples of a trimolecular reactions. Now moving on to the kinetics of trimolecular reactions, we have studied several theories which could explain, or which is explaining the kinetics of kinetics of unimolecular reactions as well as kinetics of bimolecular reactions. Now all those theories were also tested and tried for these trimolecular reactions, but none of them could explain the trimolecular reaction. So the first attempt was made by trying our collision theory, that is our simple. So the first attempt was made to use the collision theory and to explain the mechanism or to explain the kinetics of this particular third order reactions. But in case of collision theory, it is considered that the molecules, they collide, and as a result the there is a formation of the bond and reaction will take place. But the collision, that is three molecules, they colliding at the same time, the probability of all these three molecules colliding at the same time is very very rare. So, and the probability is almost zero, and hence the formation of the activated complex cannot be explained with the help of simple collision theory, and hence simple collision theory was not successful in explaining the formation of this activated complex, and it could not be applied, or it was not of further use. So after simple collision theory, again in 1916 Todt's, he suggested that trimolecular reactions, they take place in two stages. So he gave his own theory, that is Trot's theory. He suggested that trimolecular reactions, they take place in two steps, and in 1918 he proposed this theory. Basically, he said that the reaction takes place in two parts, and first there will be a formation of activated complex, and after that complex will further react with one more molecule, and as a result the final product will be obtained. So we may take the example, in order to understand this theory, we may take the example of again formation of the first, or formation of our nitrosyl bromide. So this nitrosyl bromide over there, we know the reaction. So the first step, as said by Todt's, that first a molecule of nitric oxide, it will react with 1 mole of a bromine molecule, and it will undergo a sticky collision wherein NOBr2 complex will form, which is very short half-life. That is, we have NO, and this reacts with Br2, and obviously it will be a reaction wherein there is an equilibrium. So we can write K1 for the rate of forward reaction, K-1 for the rate of reverse reaction, and we will have NOBr2. So this is our activated complex that is formed after the sticky collision between NO and Br2. And further, this complex, it has very short life, and second step would be this complex will further react with 1 more mole of nitric oxide, and as a result we can write K dash. So we will have 2 NOBr. Okay, so this is the mechanism as proposed by Todt's, and now in order to write the rate for this particular reaction, over here we may use the steady state approximation. That is, over here we have this intermediate is formed, and according to the steady state approximation, the intermediate, or the concentration of intermediate, is equal to 0. In order to find out the concentration of our NO2Cl, that is, we can write that rate of formation of NOBr2, this we can write it equal to, we can write K1 into concentration of NO into concentration of Br minus K2 into concentration of NOBr2, and that will be equal to 0. So we can rearrange this as concentration of NOBr2 is equal to K1 upon K2 NO into Br. Okay, so now we have concentration of NOBr2, and in the second step we have NOBr2 is reacting with NO again for the rate of this, that is d NOBr upon dt will be equal to, suppose if we write K dash into, we will have NO into, we will have NOBr2. So we have already the concentration of NOBr2, so that we can substitute it over here, and when we substitute it, we will have K dash into K1 upon K2 into NO remains as such, and we will have NO into Br. So we will have all these three are constants, so we can combine all these three constants and we can write it as K3, and this will be NO square, and this is Br. So basically it is a third order reaction, and over here K3 is a constant, or K3 is our constant, that is the rate constant. So the rate over here, with the help of Totru's theory, we can show that it is a third order reaction. And similarly, with the help of similar mechanisms, other reactions could also be explained. That is, suppose the formation of nitrogen dioxide, that is we have NO plus O2. So this will be the first reaction wherein NO3 is formed, and this NO3 again it reacts with again NO to give to NO2, that is nitrogen dioxide is formed. Okay, so in this way, with the help of Totru's theory, we can explain the formation of the products as well as we can determine the rate also. But there is an objection in this theory, or there is a limitation in this theory, that is, if we calculate the collision frequency by using Totru's theory, and if we look at the experimental collision theory, experimental values of the collision, then the values as obtained by this particular theory is very large as compared to the actual frequency factor, and as a result this theory cannot be acceptable, or it is not acceptable, as there is large difference, or there is a large deviation in the actual frequency factor and the frequency factor which is calculated using Totru's theory. So in order to overcome this particular difficulty in Totru's theory, 1922 again M. Bodenstein he gave a very different and more general treatment for explaining this type of trimolecular reactions, where he did not specify with the help of which pair the sticky reactions takes place, but he just generalized that when NO and oxygen molecule they are reacting, or NO, 2 moles of NO and oxygen molecules they are reacting to give 2 NO2. He did not specify that first NO and oxygen will only react. Any reaction, that is 2 NO molecules could also react, and then further it may be reacting with O2, or 1 NO 1 O2 may be react, or any possibility is taken. So he did not generalize, or he did not tell that what type of sticky reaction, or between which two pairs first the sticky reaction or the first complex will be formed, and after that trimolecular reaction will take place. So he just generalized the assumptions of Prott's theory, and as a result he proposed his theory. But also over here there was an objection, or there was a limitation in this theory. That is, the limitation is that when we take the ratio of tertiary to the binary collision, then the ratio was about 1 to the 1000. That is, out of 10,000 more collisions, only one trimolecular collision was possible, and this value also was found very large than the frequency factor of the trimolecular reactions. That is, the frequency factor, and this value was around 10 to the power 5 times larger as calculated by, or as obtained experimentally. So this value is also very much large as compared to the actual observations, and hence this theory was also not acceptable. So then two scientists named Grisnovich and Ering Young, that is E. Young, they took the help of activated complex theory, or which is also known as absolute theory. So they took the help of absolute theory. So they took the help of absolute theories of reaction rate, and with the help of this absolute theories of reaction rate, they tried to explain the dependency of the temperature, as well as they tried to explain the structure of the activated complex that might be taking place. So in this theory, basically the loss in entropy of activated complex, when the three molecules they are coming together, so when these three molecules they will come together and form a product, then there will be some loss in the entropy, and that loss in the entropy is also considered, and also the structure of the activated complex or the structure of the transition state also is considered over here. So suppose if we are considering that we are taking one example again, the same, that is the formation of nitrogen dioxide, that is NO2. It gives 2 NO2. It is considered that the activated complex which is formed will have all the molecules that are present in the reaction, and the composition, and that is the general composition, we may write it as NO2O2, and the hypothetical structure of this, the hypothetical structure is generally represented in this particular manner. Okay, where over here the directions of valencies in the oxygen and nitrogen oxide, the molecules, they are basically, it is in a rectangular configuration. So the activated complex, it is considered that it has a rectangular configuration, and as we can see that this activated complex, it has 4 transitional degrees of freedom, and out of which 1 transition degrees of freedom, it is already taken in the consideration when the theory or when the equation was formed. Again, in this structure, there are three rotational degrees of rotational, as well as there will be 3 into 6 minus 7, so there are total 11 vibrational degrees of freedom. So there were total 4 transition degrees of freedom, 3 rotational degrees of freedom, also there are 11 vibrational degrees of freedom. Now out of this 11 vibrational degrees of freedom, 1 vibrational degree of freedom will be replaced by the rotational degree of freedom. Why? Because of this particular OO bond, and over there, because of this OO bond, we know that this bond, from statistical thermodynamics, it has tendency to rotate around the axis, and as a result that vibration will be replaced by the rotational degree of freedom. So over here total we will have 10 vibrational degrees of freedom and 4 rotational degrees of freedom, that is 3 original and 1 because of the formation of this particular OO bond in our activated complex. Okay, and basically we are taking the aid of statistical thermodynamics, and basically we are taking the help of the partition functions in order to explain this particular theory. Okay, so the rate for this reaction, we are not going in detail into the derivation of all the kinetics. We are directly taking the final expressions, and when we look at the rate, then the rate according to the activated complex theory, we can write it as Kr is equal to Kt upon H Q star upon Q of O2 into Q square of NO e raised to minus E0 of RT. Okay, so this is the expression for the rate as given by the absolute theory, and over here we know that K Boltzmann constant is the temperature, H is our Planck's constant, Q star is the molecular partition function of the product divided by, this will be the molecular partition function of the reactant into E raised to minus E0 upon RT. Okay, so over here this Q star, it contains all the things, that is translation vibrational translation partition function, vibrational partition function, rotational partition function, as well as the electronic partition function if it is there, and similarly all these expressions also. So when we substitute all those terms, we will have Kr is equal to, now the expression will be bit longer, and I am putting the screenshot of this expression which you can see over here. So we have all the terms, that is we have G star upon G0, G0 square N0, where G and N are the electronic multiplicities. Then we have sigma, that is we know it is a symmetry factor, that is for homonuclear molecules sigma will be equal to 2, and for heteronuclear molecules sigma will be equal to 1. M and M0 are the masses of O2 and NO2. I, all the I's, they are the moment of inertias, and over here we have I00, which is the moment of inertia of the OO bond that we have that I have talked about. Okay, so this will be the expression, and when we combine all the constant terms together, okay, so all the constant terms could be combined together, and the expression can be written as Kr is equal to all the terms are combined together, and all the temperature terms in the numerator and in the denominator could be cancelled out, and our expression becomes G, where all the constant terms I have written it equal to G, where all the constant terms are all this you can see over here, and further we have G into T cube. I am not writing that those expressions as it will be bit longer, upon pi I is equal to 1 to 10, because there are total 10 vibrational degrees of freedom, 1 minus E minus H mu I star upon KT minus 1 upon 1 minus E raised to minus H mu O2 upon KT minus 1 into 1 minus E raised to minus H mu N0 upon KT minus 2, and we have E raised to minus E0 upon KT. Okay, this expression we can see that the rate over here is inversely proportional to the cube of temperature. So this means that as the temperature of the system increases, for a trimolecular reaction the rate of the reaction should decrease, and calculated values and experimental values also they suggest that. Now, in order to solve this particular expression, we need the values of the vibrational frequencies Vi, and to know this vibrational frequencies, it was proposed that the vibrational frequencies of N2O4 molecule having same composition, that is we are taking we are basically considering our complex as NO2 O2. Okay, so over here we are considering that the vibrational frequencies of N2O4, which has the same composition, is to be used, but obviously the structure of both are different, but the vibrational values of the vibrational frequencies are almost similar, and we can use the values of vibrational frequencies of N2O4, and only 6 values of vibrational frequencies which are less than 900 centimeter inverse, are only used. And the reason for using all those vibrational frequencies, or only 6 vibrational frequency, is that with the values of greater, that is with values greater than 1000, the expression, that is 1 minus this particular expression, the value is approximately equal to unity. Okay, so as over here also for vibrational frequency of oxygen and vibrational frequency of nitrogen, the vibrational frequency of oxygen is around 1580.32 centimeter inverse, and similarly for nitrogen oxide or from nitric oxide it is 1906.54 centimeter inverse. So over here, as these vibrational frequencies are very large, these terms will be almost equal to unity, and hence the terms in the denominator also we are taking only 6 vibrational frequencies which are lesser than 900. Okay, so our expression, that is Kr, will be equal to G upon T cube pi I is equal to 1 to 6 1 minus E raised to minus H mu I star upon KT into, we will have minus 1 E0 upon KT. Okay, so this will be the expression, and further we will group few of the terms, and then we will take logarithm. So we can take logarithm of this particular expression. So when we take logarithm, we can write ln kr. This I can take on right hand side, so we will have 3 ln of t plus minus this I can take left hand side, so we will have ln of pi I is equal to 1 to 6 1 minus e raised to minus h mu I star upon kt inverse, and then this I can write equal to, we have ln of G minus E0 of RT. Okay, and further we can take both these terms together as both has t, and we can write it equal to function of t. So we will have ln of kr plus function of t, that is equal to, and again both this I am taking together because it is only 1 upon function of 1 upon t, so we can write f1 into function of 1 upon t. Okay, so this will be the expression. So when we plot a curve of these two terms, that is ln k and function of t versus 1 upon t, that is when we plot a curve of ln kr plus function of t versus 1 upon t or versus 1000 by t, then this curve will be almost a straight line, and this straight line we can say that E0 is equal to 0. Okay, so now this value of E0 is equal to 0, again it could be used in this particular expression to evaluate the value of the activation energy and to evaluate the value of the rate constant k, and hence the theoretical rate constants can be calculated by using this particular result. And when we compare the theoretical and calculated results as obtained from this activated complex theory, then you can see over here we have the results of the same reactions at different temperatures, and you can see that at 80, 140, 280 and so on, we can see a very good coincidence of the results experimentally as well as calculated also. That is there is very small difference in all this, and also we can see that the rate dependence on the temperature also, that is as the temperature is increasing, the rate of the reaction is decreasing. Okay, so thus we can summarize that this activated complex theory, it solves the main theoretical difficulties that are appearing in the consideration of trimolecular reactions. In particularly, it explains the temperature dependence on the reaction rate. That is, with the help of activated complex theory, we can very well explain the temperature dependence of trimolecular reactions on the rate of the reaction. Hope the explanation was clear. Thank you very much.